Language models seem to think in silence and then speak. This paper from Anthropic argues there is a specific, readable place where that silent thinking lives. They call it a global workspace. And the tool that reads it is a beautiful piece of linear algebra called the Jacobian lens. Let's build it from scratch. First the intuition, then the real math, and then the actual algorithm you could implement today. Start with where the thinking happens. As a transformer processes a token, it keeps a running vector called the residual stream. Every attention block and every feed-forward block reads that vector, computes something, and adds its result back in. So the residual stream at layer L is just the input, plus everything the model has figured out so far. At the very end, the model has to turn that final vector into words. It does this with a single matrix, the unembedding, which maps the last activation onto a score for every token in the vocabulary. A softmax turns those scores into the probabilities you actually see. So the output is, quite literally, a linear readout of the final residual stream. Here is a tempting shortcut, known as the Logit lens. If the unembedding decodes the final vector, why not point it at the intermediate vectors too, and read the model's mind halfway through? In the last few layers, this works surprisingly well. But in the early and middle layers, it mostly returns garbage, because those layers do not yet live in the same coordinate system as the output. The fix is the whole idea of the paper. Before we decode a middle layer, we should first account for how the network will transform that vector on its way to the output. In other words, if I gave this layer a tiny nudge, how would the final answer move? Capture that relationship as a matrix, apply it first, and then decode. That correction matrix is the Jacobian, and it is what makes the lens honest. So what is that matrix exactly? For a single prompt, take the final activation and the layer L activation, and compute the derivative of one with respect to the other. That is a Jacobian, a D by D matrix whose entry I, J says how much output dimension I moves when input dimension J is nudged. It is the local, linear approximation of the entire rest of the network. But one prompt's Jacobian is noisy. It tangles up the model's general disposition to verbalize a concept with the specific quirks of that one context. The trick is to average. Average the Jacobian over every source position, over every later position it can influence, and over about 1,000 different prompts. What survives the averaging is the stable, context-independent map. What washes out is the noise. Put it together, and you get the central object of the paper. J of L is the expected Jacobian, the average over positions and prompts of the derivative of the final activation with respect to the layer L activation. 1D by D matrix per layer. This is the Jacobian lens. Everything else is just using it. Now we can read any layer. Take its activation, pass it through J of L to project it forward to the output space, normalize, apply the unembedding, and softmax. That whole chain is the lens. It answers a precise question. Given what this layer is holding right now, which tokens is the model currently disposed to say, either now or later? Here is the elegant part. Fold the unembedding and the Jacobian together into one matrix. Each of its rows is a direction in the residual stream, one per vocabulary token. These are the J-lens vectors. Reading out a token is then just a dot product. How much does this layer's activation point along that token's direction? These directions are the alphabet of the workspace, the things the model can actually verbalize. It helps to see how this differs from its cousins. The Logit lens is the special case where you pretend the Jacobian is the identity, that nothing changes between here and the output. The tuned lens trains a separate matrix per layer to match the final distribution. That is learned and correlational. Jacobian lens instead measures the network's own average causal linearization. Nothing is trained, it is derived. Because these are honest directions, you can also write with them, not just read. To steer, add a token's direction into the activation, and the model becomes more likely to think, and say, that token. To ablate, project that direction out, and you erase the concept. This is the causal test. If these directions are real, pushing on them should change behavior in exactly the predicted way. The cleanest intervention is a coordinate swap. Stack two token directions into a matrix V. Use its pseudo-inverse to read off how much of each is present in the current activation. Swap those two coordinates and add the difference back in. Magic is that the component of the activation orthogonal to these two directions is left completely untouched. You change exactly one thing and nothing else. Now zoom out from single tokens to the whole set of readable directions. The claim is that the model's reportable state is sparse. At any moment, only a handful of these directions, maybe a couple dozen, are active, with non-negative weights. The set of all such sparse, non-negative combinations is a union of cones. That set is the J-space, the geometry of the global workspace. Given any real activation, you can ask how much of it lives in the workspace. That is the distance to the nearest point in J-space, found by a greedy matching pursuit that picks the best handful of directions. Strikingly, this reportable component is small, under 10% of the activation's total size. The workspace is a thin, structured slice of a much larger internal state. So how do you actually compute this? The beautiful thing is that all the cost is one time. You estimate the Jacobian matrices once per model, offline. After that, reading any layer is a single matrix multiply. Let's walk through the real procedure, step by step. Step 1, gather gradients. For each prompt, run a normal forward pass and cache the activation at every layer and position. Then, for each output dimension, inject a gradient of 1 into that dimension at every position and backpropagate. AutoGrad hands you, for free, how that output dimension depends on every earlier layer. That row of sensitivities is one row of the Jacobian. Step 2, average. Then a prompt, average each sensitivity over all the positions it reaches. That gives one Jacobian estimate for that prompt. Then average those estimates across all the prompts. The result is J of L, the mean Jacobian for that layer. The averaging is what turns noisy, per-context gradients into a stable, general map. Step 3, use it. To read a layer at inference time, multiply its activation by the stored Jacobian, normalize, apply the unembedding and softmax. Sort the tokens by score, and you are reading the model's disposition at that depth. One matrix multiply, no gradients, essentially free. A few implementation details make it work well. Target the second to last layer, not the final one, because the last block behaves like a motor stage that just commits to the answer. You need one backward pass per output dimension, but those batch efficiently. And while the default uses about 1,000 prompts, the estimate is already robust from only 10. It is far cheaper than it first sounds. Step back and notice why this is more trustworthy than a trained probe. Tuned lens learns a map to match the output, so it can cheat by skipping straight to the answer. The Jacobian lens is not fit to anything. It is the model's own average linearization, read directly off its gradients. It is causal by construction, and it costs one pre-computed matrix per layer. So what does it reveal? Hidden, intermediate reasoning that never appears in the output. Give the model a chained arithmetic problem, and the lens shows the running totals lighting up at successive layers before the final answer. In a multi-hop question, the bridging entity it needs, but never says, appears inside the workspace. And with non-English prompts, the intermediate concepts often surface in English. Why call it a global workspace? Because it behaves like one. The contents can be reported, modulated, reasoned over, and broadcast to later computation, and only a selective few things are held at once. The strongest evidence is causal. When you ablate the J-space component, the model's internal multi-step reasoning breaks, but its raw ability to parse text and recall facts stays intact. And this is where it matters for safety. Because the lens surfaces thoughts before they become words, it can catch things the model is thinking but not saying. A flicker of knowing it is being tested, or a quiet intention it never verbalizes. It is a cheap, always-on monitor, one matrix multiply per layer, pointed straight at the part of the model that is trying to speak. So here is the whole idea in one breath. Take the average gradient from a layer to the output, and you get a linear map that turns any hidden activation into readable tokens. That map reveals a sparse, causal, global workspace, the part of the model that thinks in words. It is simple, it is cheap, and it might be one of our best windows into what these systems are actually doing. If that was satisfying, subscribe for more papers decoded in full.